Section 20.1, Crystal Field Theory. E. Tetrahedral complexes. In a tetrahedral complex, there are 4 ligands. And these 4 ligands are modeled as 4-point negative charges. 1, 2, 3, 4. So you need to draw a cube first, and then put this 4-point charges on these 2 corners, and then on the bottom, these 2 corners. Now let's look at the d orbitals. There are 5 different d orbitals. dzx, dyz, dxy. They belong to this T2 symmetry species in the tetrahedral point group. These 3 have the same energy. Now let's look at these 2 orbitals, dz squared, dx squared minus y squared. They belong to this E symmetry species in the tetrahedral point group. And here E means doubly degenerate. Now, let's compare the energy of these 3 d orbitals and the energy of these 2 d orbitals. These 3 have higher energy than these 2. Why is that? Again, in crystal field theory, we just model the ligands as negative charges, 1, 2, 3, 4. And then we'll just look at the distance between the d orbitals, the lobes of the d orbitals, and those negative charges. So over here, let's say, well, this lobe is roughly here. The distance between this lobe and this negative point charge is roughly 1/2 of the silence of the cube. All right? Same here, 1/2, 1/2, roughly 1/2. Okay, just approximation here. Now let's look at this distance. This distance is roughly 1/2 of this diagonal, and this diagonal is 1.414 times the silence. It's the square root of 2 times the silence. And then square root of 2 divided by 2, that's 0.707. So this distance is roughly 0.7 times the silence. Over here, the distance between this one and this negative charge is roughly 0.5. So now you can tell the repulsion between this negative charge, and supposedly if you put an electron here, the repulsion is going to be greater in this scenario than in this scenario, only because the distance between this lobe and the negative charges is closer than this situation. So same here, if you look at those lobes, they are roughly 0.5 silence away from the closest negative charge. All right, so roughly 0.5. So that's to roughly 0.5. Roughly 0.5 times the silence. Same here. Now again, look at this. This is roughly 0.7 times the silence. And also, if you look at the distance between this negative charge and this lobe, it's also roughly 0.7 times the silence. So, semi-quantitatively, I just explained why these 3 d orbitals have higher energy than these 2. But now, if we look at the energy splitting between these 3 and these 2, it's smaller. It's actually much smaller than the splitting in the octahedral complex. This is because in the octahedral complex, these 2 orbitals point directly to the negative charges. Remember, in an octahedral complex, you have a negative charge right here and one right here. And also, in the octahedral complex, you have negative charge right here, here, and here. So the lobes of these 2 d orbitals in an octahedral complex point directly to the negative charges. Now, in a tetrahedral complex, that's not the situation. These 3 orbitals have higher energy because their lobes are closer to the negative charges. But I want to point this out. Their lobes are not pointing directly to the negative charges. So the energy splitting between this T2 orbitals and this E orbitals is smaller, or even much smaller than the splitting in an octahedral complex. So in an octahedral complex, we use delta O for the splitting. Here, delta T. So now you're looking at the energy diagram here. This is a free transition metal center. And now we put this free transition metal center in a tetrahedral environment. It's now surrounded by 4 ligands. And then the energy of the d orbitals splits into this higher energy T2 level and the lower energy E level. You have dz squared and dx squared minus y squared here. You have dxy, dyz, and dzx up there. Over here, this is again called the Barry center. So the T2 orbitals, 3 of them, sit 0.4 delta T higher than the Barry center. The 2 E orbitals, dz squared, dx squared minus y squared, sit 0.6 times delta T below the Barry center. And again, this delta T is much smaller than delta O. How much smaller? Delta T is roughly 4/9 of delta O, or 44% of delta O. It's even less than half of delta O, only because the 3 d orbitals with this T2 symmetry do not point to the negative charges directly. And again, I want to emphasize here, in a tetrahedral environment, there's no inversion center. So do not put a G here, do not put a G here. So it's just E and T2. In the octahedral complex, yes, there is an inversion center, and then you will have to say EG sits above T2G in a octahedral complex. So now, again, let's look at the tetrahedral complexes. They're almost always in the high spin electronic state. This is to reduce the electron-electron repulsion. This is because delta T is much smaller than the electron pairing energy. All right, remember in the octahedral complexes, delta O and P are in general within the same range between 10K to 30K wave numbers. In this case, delta T is only 40% of delta O. So typically, delta T is much smaller than the electron pairing energy. Now let's look at the low spin cases and high spin cases in a tetrahedral complex. So low spin case. In a low spin scenario, we try to pair up the electrons in the lower energy E orbitals. So we put the electrons in the dz squared orbital and the dx squared minus y squared orbital first. When we have 3 electrons, they occupy the lower energy E orbitals. We have only 1 pair of electrons, well, in one of the 2 d orbitals. And we have this LFSE plus the electron pairing energy. So this is negative 1.8 delta T plus P. Why negative 1.8 delta T? Okay, so this E orbitals set 0.6 delta T below the barycenter. And you have 3 electrons, 3 times negative 0.6. That's negative 1.8. And then you have 1 pair of electrons. Now, for the electrons, you can put all of them in the E orbitals. We have 2 pairs of electrons. Therefore, you see 2p here. And then 4 times negative 0.6 is negative 2.4. What about 5 electrons? Again, you put 4 electrons in the E orbitals, and then 1 electron in the T2, one of the 3 T2 orbitals. All right? So again, you have 2 pairs, 2p here. What about this delta T? You have 4 times negative 0.6 plus 1 times positive 0.4. So that's negative 2.0. Now you have 6 electrons, 4 times negative 0.6, 2 times positive 0.4. Put them together, you get negative 1.6 delta T. Again, there are 2 pairs of electrons, so plus 2p. Now let's look at the high-spin scenarios with 3, 4, 5, or 6 d electrons. I'll let you just pause here and see if you can make the same predictions as I made here, over here. So again, I mean, you just need to calculate this LFSE carefully. You know, you need to count the number of E electrons, the number of T2 electrons, right? And then you multiply this number by negative 0.6, multiply this number by positive 0.4, sum it up, you can get negative 0.8. And in this high spin scenario, and this one, I don't think we need to pair up electrons, right? So in the high spin electronic state, if you have only 5 or less than 5 electrons, each of them can occupy a different orbital. Over here, you have 6 electrons, so inevitably you'll have to pair up 2 electrons right here in the lower energy E orbital. That's why you have 1p here. All right? And then again, we use high energy, high spin minus low spin. So we got something like this. Okay, it's going to be delta T minus P, and then 2 times delta T minus P, 2 times delta T minus P, delta T minus P. So if you look at this 4 expressions, they are just similar to this high spin minus low spin for the octahedral complexes. The only difference here is you replace delta O with delta T here. But we learned that delta T is much smaller than delta O. Delta T is roughly 44% of delta O. It's even less than one half of delta O. So in this case, delta T is almost always less than P. So these 4 are almost always negative. That means high spin state almost always have lower energy than the corresponding low spin states. So that's why in a tetrahedral complex, without thinking, you can predict the high spin state is favored energetically. Okay, again, this is just because delta T is very small. It's typically much smaller than the electron pairing energy, so you really want to put the electrons in different d orbitals whenever you can. Is it possible for delta T to be greater than the electron pairing energy? Well, it's possible, but it's extremely rare. Okay, so you'll have to have a really large delta T. For example, you need strong field ligands. And also, I think you need 4D or 5D transition metal center so that the interaction between the metal and the ligand is more significant. And also, if you have a large oxidation number on the transition metal, and then it's possible for this delta T to be greater than P. So now in conclusion, tetrahedral complexes are almost always in the high spin electronic state because of their small delta T.